Hello friends, here in this video we are going to see a problem in which a body is being subjected to two mutually perpendicular stresses, and for that here we have a question, and this question belongs to principal stresses and planes. So I'll write the data. The principal stresses at a point in the section of a boiler shell are 120 megapascal and 30 megapascal, both tensile. So the first stress which is given, we have to take it as stress in x direction, that is sigma x, as 120 megapascal. So it is 120 Newton per mm square, and the second stress is 30 megapascal, so it is sigma y, 30 Newton per mm square, and since both are tensile, so they are positive. Otherwise, if any one would have been negative or both, if they would have been negative, then here we would have written negative sign, but since it is tensile, so they are positive. Now find normal stress, second tangential stress, and third resultant stress, which is sigma suffix r, across a plane inclined at 50 degree to 120 megapascal stress. So theta is 50 degree. And now with the data available, let us try to get the solution to this problem. In the solution part, first we need to draw the diagram. Now this is the member which is given, and it is subjected to stresses in two directions, that is two mutually perpendicular directions. They are sigma x and sigma y, both are tensile. So sigma x, this is 120 Newton per mm square. Sigma y, it is 30 Newton per mm square, so perpendicular. Now, so this is the part of the boiler shell which is given in the problem, that this is a section, or we can say a part of boiler shell given in the problem. Next, we have to find out normal, tangential and resultant stresses across a plane, that is on the plane which is inclined at 50 degree to 120 megapascal stress. So this is the 120 Newton per mm square stress, and it is inclined to that at 50 degree. So to this it is inclined, means the face on which 120 Newton per mm square is acting, to that face the plane is inclined, and this angle is 50 degree. So here theta value is 50, and the next thing is we have to calculate the normal stress first, then tangential, then resultant. So starting with the normal stress, I'll write down the formula, that since normal stress is given by, now the formula is, it is sigma x plus sigma y by 2 plus sigma x minus sigma y by 2 and into cos 2 theta. So this is the formula to be used if we are having stresses in two mutually perpendicular directions. This is the formula of normal stress. So here I'll go on putting the values. Sigma x is 120, sigma y 30 divided by 2, and in this case, since both the stresses are positive, we are taking the positive sign. Next, sigma x 120 minus sigma y 30 upon 2 cos 2 theta, that is 2 into 50 degree. So sigma n, the normal stress value, it comes out to be 67.18 Newton per mm square. So this is the first answer. Next we have to calculate tangential stress on this oblique plane. Therefore tangential stress is given by sigma suffix t is equal to sigma x minus sigma y by 2 into sine 2 theta. So therefore sigma t is equal to sigma x 120, sigma y 30 divided by 2 into theta is 50 degree. So therefore the tangential stress answer comes out to be 44.31 Newton per mm square. This is the second answer. Next, after getting tangential stress, we need to find out resultant stress. So I can say that therefore resultant stress is given by sigma suffix r is equal to root of sigma n square plus sigma t square. So therefore sigma suffix r is equal to root of sigma n, that was 67.18 square, plus sigma t 44.31 square. So from this I'll get the answer of resultant stress. It is 80.47 Newton per mm square, and this is the third answer. So here in this question we were asked to calculate the values of normal, tangential and resultant stresses across the inclined plane, that is the oblique plane which was inclined. So we have found out all the values, starting with normal stress 67.18 Newton per mm square, then tangential stress 44.31 Newton per mm square, and at last resultant stress on the oblique plane. And with this we complete the problem.